Going on now to the last topic in Chapter 4 that we'll be covering, Section 3 on Logarithmic Functions. Now, logarithms used to be used a lot. I can recall when I was in high school, we'd have in the back of our algebra books tables of logs. That we'd find the log, then we'd go to the tables, then we'd multiply them out. But of course, now that we use calculators, these log functions are built in, so it's much easier to do, but we're still going to take a look at it. Logarithms are simply a new language for old ideas. It's a special case of exponents. So we'll start off with what is the definition of common logarithms. Now, the common logarithms we use for base 10, which is the system of mathematics we generally use. We have 10 symbols, and that is used to make up our number system. So, let's take a look at this, and I have something I'd like you to copy down. Now, this is something we should be familiar with, exponential form, where we have 10, which is our base, raised to an exponent, the 2, again, which is our exponent, and that equals the answer. So this is the general form. Base raised to an exponent equals an answer. And then we have the log form of the same thing. We're saying log base 10 of 100 equals 2. Well, the general form then of the log is log. There's where your base goes. There's your answer. And this equals an exponent. So logs are exponents. And this is what they're showing you here. That your y is your exponent. This is sort of like the 2. They have this a little backwards. Now the log, and since this is base 10, and if they don't write it, this is the common log, which they aren't writing, and they're saying now this answer is going to be 100. But they're just giving it to you here in a general form. And this form we're already familiar with. This is 10. Again, our exponent is 2. And our answer here is the x, which is 100. So this is, I think, a good reference for you to include in your little booklet. And we'll take a look at the examples now. So we can follow along now with example 1. To find the log of, let's say, 10,000, we ask ourselves, to what exponent must 10 be raised to produce 10,000? Well, that exponent is 4. So it would be 10 to the 4th equals 10,000. Now to put that in its log form, it's going to be log. Your base is 10. And your answer is 10,000. And the exponent is 4. So there's the logarithmic form. Now, there are a couple little tricks that you need to be careful of, and that is the log base 10 of 1, that is 0. So what did we say if we have base 10 to the 0 power is 1? So this is what they're showing. Now, when we have a negative exponent, remember that gives us the reciprocal of what 100 would be. 100 is 10 to the second. So if we had that to the negative 2 now, this would be 1 over 100. And that's what they're showing here. And we write it in its decimal form. Now, in writing this now, log base 10, this is the answer. And if we want to convert 10, the square root of 10, to its fractional exponential form, remember there's a 2 there, and there's a 1 there. We don't write the 2. This is to the 1/2 power. So therefore, we get this. Log base 10 of the square root of 10 is 1/2. I wish they would use these diagonal lines to show their fractions, but of course that's how they're doing it. Going on to example 2, they're saying the log of base 10 of a negative 25. Now, if the exponent that we must place by 10 to get it to be a negative 25, there is no such value. So we say that there are no exponents that will produce a negative 25. So therefore, logarithms of negative numbers and 0 are not defined. So anytime you get a value that might give you a negative logarithm like this, that is not defined. Now in example 3, they want you to do some brainstorming here. They're saying we know that the log of 359 must be between the log of 2 here and the log of 3. Why? Because this would be in here somewhere. So it would be the log base 10 of this is what exponent? Well, again, if it were 100, it would be 2. If it were 1,000, it would be 3. So we know that this number is between 100 and 1,000, so it must be somewhere in the middle. And in fact, if you put this into your calculator, there is a button log, and it appears like this without the 10, and then 359, you have to put an extra parenthesis there to close that. Hit enter, and it gives you 2.551. So you see that's sort of in the middle between a 2 and a 3. So in letter B it says when 10 is raised to a negative exponent. Now remember, you can have negative exponents. The result is a number that is less than 1, that is, some sort of fraction. Consequently, the logarithms of numbers between 0 and 1 are negative. So for instance, the log of this, which is a number less than 1, is a negative. Now again, if you put this into your calculator, you can be checking these and practice how to use your calculator to get logs. Now here we're going to take a look at natural logarithms. In natural logarithms, we use the base e, which we've defined just recently, rather than base 10. Now these have a special notation where if you just see LOG with nothing after it, this is base 10. Now for natural logarithms, since this was originally defined in Latin, Logrimus naturalis, they use the letters LN. For natural log, they just write it in reverse. And keep in mind that would be base E. Often they don't write the E as you see here. Okay? So this means base e to the exponent y, and x is the answer. And again, keep in mind that anything to the 0 power is 1, something we've just done recently. So in example 4, we're going to use our natural log key on our calculator and find the natural log of 85. Well, we put NL, 85, close the parenthesis, enter, and you should get this. And if you take this and take E and then caret, put this exponent in and hit enter, it should give you rounded to 85. And let's try this one now. Natural log 0.38, close the parenthesis, enter. It should give you a negative exponent, rounded, that if you put that as E, caret, to this, including the negative, you get approximately 0.38 rounded. Now, in example 5, they're saying, and this is something a little easy, but it's more of a definition, you don't need a calculator to find the natural log base e of e to the 8th power. You just need to ask yourself, to what exponent must e be raised to produce e to the 8th power? And the answer is obvious, they're saying. It is 8. So the natural log of e to the 8th power is 8. And there's a rationale for this, is that when, again, natural log is base e, and you have this over this is a 1, so 8 equals 8. This part is 1 here. Base e, the answer is e, the exponent is 8. So they're not making this super clear, but whenever you see this arrangement, again, by definition, this is 8. Now, there are other logarithm systems other than base 10, the common log, or the natural log base e, that as long as the base a is not equal to 1, it can be replaced where the 10 would be or the e would be. So definition of logarithms to a base a would be a is raised to any exponent gives you the answer. And here's the other form, the general definition of logarithms, where you could put an e here, you could put a 10 there, you could put an a there, but it cannot be a 1. That's not allowed. So we have been using base 10 here, or base e. Now we're using base 2. 2 is our base. 4 is the exponent, and 2 to the 4th power is 16. So we write it in logarithmic form, log base 2 of 16 equals 4. Remember, 2 is the base, 4 is the exponent, 16 is the answer. And this is what they're going about here. And more explanation here. Okay, let's go on to example 6 now. This shows several statements written in both exponential and logarithmic form. So let's spend some time looking this over. And let's keep in mind that little pattern we set up in the beginning of this lesson, that in its exponential form we have the base raised to an exponent equals an answer. And in the logarithmic form we have the log of a base of an answer equals the exponent. So here it works out very well. 3 to the second equals 9. Log base 3 of 9 is 2. And we can go down, and I don't want to read all these things to you. I have this chart in your booklet. Again, I might point out that anything to the 0 power, remember the exponent is 1. So the log base e of 1 or natural log of 1 is equal to 0. Remember, these are the exponents out here on this edge. And over here, these are the answers. So you'll have to study this. This is something you should memorize. It's going to be absolutely important to know how to convert from exponential form to logarithmic form. And if you're ever stuck, then use this little sort of flow chart here. I think it's very helpful. Now, for properties of logarithms, we're going to develop some definitions as we look at them. And remember, our a, which is our base here in many cases, cannot equal 1. And r can be any real number. Now we said, if our base is a, and the answer is 1, the only answer that it could be is 0. Any base to the 0 power is 1. So this is an important definition. Now, we also looked at this before. When we have the log, base a of a, now remember, there is an exponent by this a, even though we don't write it. It's a 1. And we said when this is in this arrangement, then whatever the exponent is, that's what that equals. Now here's the extension of it. We have the a and the a raised to the r power, because this part is 1 here as well. R equals r. So we had this, if you recall, we said this to the 8th here. Earlier. We just didn't write the base e. So this is an example of what we've done before as a definition, and here we're seeing it again. This is another configuration of it. When you see it like this, where a is raised to sort of a funny logarithmic power up here, but there's an a there, there's an a there, there's the answer x. It is a modification of this, and here x equals x. So these are some properties, some are by definition, and we'll get to use them. Now we're going to look at some of the rules that govern the product, that's multiplication, the quotient, that's division, and then the power of properties of logarithms. Well, to go way back, when we have something like this, x to the second times x to the third, our bases are the same, what do we do here? Now, do we multiply these or do we add them together? And the answer is we add when we are multiplying variables. We add their exponents. So this is going to be x to the fifth. Now, they're also showing that if in a log form, we could have log base 2 to the 16th. Well, another way of showing that 16th here is that it's 2 times 8. But when we're dealing with logs, we are going to add, and that's what they're showing here, that this is x times y. We treat this multiplication as actually addition. So when we're dealing with logarithms, and it indicates here multiplication, we expand that. This is sort of the condensed form. We give it expanded form, which is called the product property, by adding our factors together. It's a little bit related to this. Now, if we had something like this, x to the 5th divided by x to the 2nd, what would we do there? We would subtract and get x to the 3rd, bringing that up. Well, anytime we want to show division, and we're dealing with exponents, we're going to illustrate that or do that by having it as a subtraction. So what was in the denominator, we subtract. This is called the quotient property. And then the other property is when we actually have an answer that's raised to an exponent, it's sort of like this, x to the 2nd, now raised to the 3rd power. To do this, we don't add, we multiply. And this then becomes a funny kind of x there, x to the 6th. So we indicate multiplication, which is the power property, by taking our exponent and moving it in front of the log. And there is its place. So now this would be r times this, which is the power property, and that's how it relates. And if you look to your textbook, they're showing you how all these are defined using what I've just shown you. So let's go on to example 7. And what they want us to do is, using the property of logarithms, we can write each of the following that are in the expanded form as a single logarithm. So there is example A here, and I want to work it with you, and of course you're taking notes. So there we see it in the expanded form. Well, in the condensed form, we write log base A, but now we want to indicate, because of addition, that we're going to multiply x times x minus 1. So again, when we have it in the expanded form in addition, in its condensed form, we can show it through multiplication. Now keep in mind, if you see something like this and they want it in its expanded form, we do just the opposite. So in letter B now, we see in its expanded form there is subtraction. And what did we say this is defined as? Division. So we write it log in its condensed form. This will be our numerator. And then this is going to be our denominator. And there they're showing it there as well. Now in letter C, again, this is expanded form. We're going to put log base A of 9. Now it's plus 5, and in that video we said, or that previous slide, where the 5 was out in front of the log, that's going to go to its exponent there. So this becomes x to the 5th power. That's, we take the exponent and put it in front of log because this is raising it to a power. And this is what you see there. Okay, and of course the proof is when you do this in your study plan. Now they do give cautions in our book here. Now notice this was kept in parentheses. This is the proper way to express this. It is not equal that if you separated them here. This is not multiplication. This is addition of something. So be careful about that. Now, for example 8, they want you to assume that log base 6 of 7 is approximately this, and log base 6 of 5 is approximately that. They want you to use these properties of logarithms to find each of the following. The log of base 6 of 35. And this is written clearly, but let me just go over it here on the side. Log base 6 of 35. We can take log base 6, we can take our 35, put it into its factors. 7 times 5. We can now spread that out and get log base 6 of 7 plus, since this is multiplication, log base 6 of 5. And we have these values. So if we add these values together, we then get our answer. Now for this next one, instead of writing it, let's just follow it. And then remember it's 5 divided by 7. So we'll take the log of base 5, which is this, subtract from it the log of base 7, which is this. I'm sorry, base 6 of 7. And when you do the subtraction, you get this. So a little tricky, but it's showing you, and again, they wrote this nice, 5 over 7. So you're going to subtract the value for 7 from the value for 5 because of division here, and you get this. Now here we have the log base 6 of 5. We're going to take our 3 as an exponent and put it out in front, which they do here. So then we're going to take our value for 5 here, which is 0.90, multiply it by 3, and we get this for a value. Now for number 6, since from our definition we had earlier, log of 6 of 6, remember there's a 1 there, we said that just equals 1. So we didn't have to use these. And when we have something like this, that the answer, when it's 1, any base has to be to the 0 power to get an answer of 1. So a couple of little things, and I know you're getting anxious to want to try some of these, so you can test your mastery was the word I was looking for. Okay, change of base theorem. Now, for any positive number, a, with x, and remember a as a base cannot be equal to 1, we have a change of base theorem, which is what I have here, which in essence is saying that if you have a base, whatever it happens to be, we can convert that to the natural log of x divided by the natural log of a. Now, we could also convert this, as they will tell us here shortly, that we can do the log of x divided by the log of a, whatever the a is. Now, what we've done is changed it. It's called change of base. We've changed it from whatever base it was into values we have on our calculator. We could change it into natural logs or common logs. So in example 9, they're giving you log base 7 of 3. Now, that's not found in our calculator, but we can go to natural log of 3 divided by natural log of 7. And that gives us a nice answer here. Now you can try that as log of 3 divided by log of 7. And that works out very well. Again, I'm wondering why they're not showing us that both of these can be used for change of base formula. But again, you have some notes. Put that in your booklet. All right, let's go on to example 10. Now, in example 10, they're talking about natural science, and I used to be a biology teacher, as I've mentioned, and I never used this formula, but here it is. It says we can find diversity within a community by using what is called the Shannon Index. And it's listed by this, where if you know the number of species and then the individuals within that species, and it's found out by using this particular formula, and we're talking about a owl that may eat this, what is the index of diversity? Well, there are this many rats, this many mice, and again they've done a survey, I'm assuming, to get this, and then they have birds. So to find the index of diversity in this community, we're going to define our n sub 1 as this, n sub 2 is this, n sub 3 is this, and then when we add them together, we get 2,000. So we put the 2,000 where the n's are, and then we find the log of these various things, and then we're going to put this in our calculator, and it just seems to get a little tedious here, but eventually you end up with this. I don't believe we'll be giving you anything like this in our work, but they're just showing you where this fits into natural communities. Now, we're now going to look at what we call logarithmic functions. We did already study exponential functions. We're going to look now, and in a sense, this is the inverse. If you recall, when we had those two formulas, logarithmic formula and exponential formulas were actually inverses of each other. So what do they look like when we graph them? Well, if we were to graph, as we see in example 11, this is the exponential function of e, and we've done that already. We're now going to put the graph of this, and we're saying it's its inverse. Now, when we do that, if we had a graphing calculator, we would see that if we did this first one, of course, this is our typical shape of e to the x power. Now, if we were to plot and then graph the natural log, remember it's base e, and then have that of x. Remember, that's our inverse function. The graph doing various points ends up looking like so. Now it goes through 1, and it will go through 2.7 about there, and it looks like so. And you might say, looking at these, one is the inverse of the other, and we have an axis of symmetry that happens to be y equals x. Again, that's a 1x, so our slope is over 1 up 1. That is our axis of symmetry, and if we folded the paper over to this line, you'd actually see that this graph lies on top of this graph. In fact, I should have a link up here that shows you some work I did to prove this. They're not giving us very much background here, but remember that the exponential form and its inverse is the logarithmic form, and that's what they're describing here as well. And I have much of this in your booklet that you can use as a reference. So exponential function, logarithmic function. Now whether it's natural log or any logarithmic function, one is the inverse of the other. And let's also mention this, that for this, remember the x-axis was the horizontal asymptote, and there was no vertical asymptote here. While for the logarithmic function, the y-axis is the vertical asymptote, and there is no horizontal asymptote. If you can even understand what I'm saying, that is a plus for your mastery at this time. Now this wraps up chapter 4 of what we're going to do, and it was sort of a review because what we've done here in one lesson, in other courses I've taught, we spent 3 or 4 lessons on just this material. So we're doing it in sort of a review way, a brief overview, and not going into it in great detail.